All right, so thank you very much for coming here. I am gonna just talk a little bit about the a little lecture that I gave. I think it's a lecture that is interesting enough to record, so let's go through it. So we're gonna talk about discrete sampling and the phenomenon of aliasing and how this affects control systems in general. So let's get started. So I'm gonna go through. This is a little bit long, so I'm gonna kind of break it down into what we're gonna look at. So first, we're going to talk about a practical example of the aliasing, and this is a piddler device that I actually am going to describe in detail how to make it. And then we're going to talk about how it works and why it works, and the Nyquist channel sampling theorem, and why the Nyquist criterion makes this effect that we see in the demonstration work. And then after that, we're going to go and talk about a little bit on the application side and how this can actually affect devices that you build and how you can mathematically model this so you can actually do some interesting modeling uh, on the engineering point of perspective. And I think it's interesting also to add that we can interpret the z transform, and it's kind of simple. So okay, so let's get started with the demonstration. So I built this little device, and unfortunately, I can't really show the device for you because, well, this is just a video, but this is the best that we can do. So let's get started. So on the left, you have a picture of how the device looks like, and I'm gonna have a video in the next slide. And on the right, how the device works, and it's actually quite simple. So we have a little water tank, and the water tank has a little pipe that connects a coffee machine pump. The coffee machine pump is actually self-priming, so you don't need to worry about submerging this little pipe. So it can actually come from above, which is kind of useful. And so the coffee machine pump is a piston that moves back and forth. And when it moves back and forth, it's connected to a check valve. So every forward stroke, it will move a slug of fluid forward. But every backward stroke, the check valve is going to shut off. And then you don't get any backwards motion of the fluid that has already made outside of the pump. And because there's a void now, you actually get suction from the opposite side, and then you keep on doing that, and you get a back and forth motion of the fluid that moves the fluid forward in slugs towards through this pipe. So because the fluid is doing this back and forth motion, it actually generates an acoustic wave, and this acoustic wave is seen over here as a fluctuation in velocity. And this fluctuation in velocity actually makes it makes it easy to form droplets at a constant rate, which is important for the sake of the demonstration of the piddler. Um, so you generate droplets at a constant rate, and then we have a stroboscopic light that allows us to see the droplets at the same kind of a frame rate as we're generating the droplets, and then we get a very interesting effect. And the effect is absolutely amazing when you're there. It's like you don't really notice any jitter, any flicker. You just see the droplets going against gravity, which is absolutely amazing. So I really recommend you do check this out. I'm gonna leave a link in the description of some of the write up that I did on this, and yeah. So with that, I'll actually show a little video of the device. So let me just show the video. So you can see here that the droplets seem to be moving backwards, towards the nozzle, which is just not really possible, right? And the effect is a visual effect. And of course, when you're taking this with your phone, this video with your phone, you can actually see that this is an effect because you see this kind of a rolling shutter effect. And this rolling shutter is because the phone itself is capturing the frames at a rate that is different from the rate of flashing of the stroboscopic light. You see the strobe light is over here. So I think this is an absolutely amazing demonstration, and it's just something that it's quite magical when you see it. But of course, you have to build it by yourself. So here I'm actually changing the rate of flashing. So you saw that before the rolling shutter was upwards, and now the rolling shutter is downwards. And you actually see that the downwards motion of the droplets follows the rolling shutter, which is quite cool and not really intended. And So now the droplets look like they're falling in slow motion. Okay, so this is a beautiful, but let's move on. So how does this work, right? So this is different. This little video here is actually different from the former one because it's captured with an actual high-speed camera, and the high-speed camera can see everything. So it's not like just doing a nice effect. It's actually seeing how the droplets are forming and falling exactly how they are. So what I'm gonna try to explain in a more qualitative manner is what happens when you start skipping frames of this high-speed footage. So we capture, let me show back here, we captured this video at 840 frames per second with a phantom high-speed camera, which I'm actually quite grateful for because, it's not like every time you get access to a nice high-speed camera. So, okay, so I'm showing here, so every strip here is actually one of the one frame of the video. I'm showing every second frame, so this is effectively like I'm showing the footage at 420 frames per second. And you see this line here, it tracks a droplet. And you see that the tracking of the droplet looks like an inverted parabola. And this makes sense because the droplets are falling, and you probably know that the equation of motion under gravity is a parabola. So this is why they look like a parabola. Now, in order to make this more like understandable from the signal processing standpoint, we're going to make each droplet a sample, and we're going to focus on a strip. So kind of imagining that when this droplet goes through this strip, it exits the frame, and then you kind of have a new sample, a new droplet coming from above. So if you do that and you connect the dots, you see the sawtooth wave, which is the dashed yellow line, but the samples that you're getting are the diamonds. And you see that you don't really get the sawtooth if you connected the diamonds, because here you're skipping all of this motion because it just didn't capture that frame, those frames, right? So you get the sawtooth wave, but it is already kind of smoothed out by this sampling effect, if you will. Okay, so, and you see here the black line looks like that. Okay, so now I'm going to skip 3 frames, and I'm going to show every 4th frame, which means that I'm having the sampling rate. And if I do that, then I have this inverted parabola that now seems to go faster. But if we now focus into the strip as we did before, we get this kind of, it looks like it's faster as a sawtooth wave, and this is just because we're capturing the frame rate slower, so it looks faster to us when we play back the video. But the problem here is now that we have only 4 samples per frame. So it's not really a problem. We can still resolve the motion of the droplets as being net downwards, but it's already becoming very difficult to discern. And if we connect the dots, we can see that we get even more smoothing of this sharp sawtooth waves. So this is kind of an effect of the sampling as it becomes poorer and poorer. So if now we skip every 7 frames, and then we show every 8th frame, then we get this true trajectory of the droplets, which is the yellow line. But now if we focus on the strip, you get this effect where the droplets seem to be jittering back and forth. And if we connect the dots, we can see the comparison between what would happen, the black line, if you connected the dots versus what would happen if you would just make the true trajectory of the droplets plotted here, which is the dashed line, the yellow dashed line. So that's a very interesting effect, and it shows that we are at the brink of not being able to resolve this effect. Okay, so this is what happens if we decimated the frames of this capture even further, and now we show every 13th frame, and you can see here that the true trajectory of the droplets is still downwards. The parabola looks like it's falling faster, but that's just the effect of showing a larger delta t between the frames. So this looks like to us like it's falling faster, but you can already have a sense that this is weird. It looks like the droplets are actually moving upwards. So they're still falling, but they look like they're going up. And this is the effect that the decimation of frames or missing a lot of stuff in between gives to us when we have a signal that is of a single frequency, as in this case it is, because we use the coffee machine pump to generate the droplets. And we also satisfy the Rayleigh plateau criterion, which is something that I talk about in length in my website. Okay, so if we look at the strip again, we have this, the sawtooth is the true waveform, but the samples give us this waveform that looks like it's actually moving upwards, or the direction is wrong. And this is what happens when you're sampling. You might sometimes get the direction wrong, and in this case you get both the direction of the phenomenon wrong, but also the frequency wrong. So the frequency is actually very fast, but you're seeing this very slow wave. So this is like this slow motion effect that you get when you do this strobe light. Okay, so now I'm showing every 14th frame, and this basically ends up matching exactly the rate of generation of droplets, which means that now the droplets look like they're not moving. And this is a very interesting effect. And if we show every 15th frame, which means that we're lowering the frequency even further, we now we have this effect where the droplets look like they're falling in slow motion. So that's very cool. So now let's try to mathematically describe what's actually going on. So I'm gonna show a chart that is called the folding diagram, and we're gonna see why it's called the folding diagram. And this is a chart where we have the true frequency in the x-axis, so this would be the phenomenon frequency, and in the y-axis we have the apparent frequency of the phenomenon as it looks to us when we sample it through our camera, our data acquisition system. It could be an Arduino, analog channel, whatever it is. And this 45-degree line, this dashed line, it indicates what would be the correct effect. So if basically any point that lies in this line means that the true frequency, whatever it is, was correctly identified when we look at the signal through this discretely sampled framework. So I'm going to claim here that, so I'm going to just replace the FA and FT because that's a little simpler notation. But I'm going to claim here that the limit, that there is a limit to what frequencies we can resolve. And this ceiling, it turns out to be half of the sampling frequency Fs. So that would be a ceiling. So anything between 0 and the sampling frequency appears to us as the correct frequency, which is good. So for example, here would be how it would look like. We have a lot of samples per cycle, which means that we can, if we just connected dots, we would see the same kind of sine wave as maybe a little jagged version of it, but it's or like a little low poly version of the sine wave, but still the correct frequency of the sine wave. If we are more up here, you see that now we have less points per cycle, but we still have more than 2, which means that we can actually kind of, if we connect the dots, we can have something that still resembles the sine wave. And this means that we can still resolve the frequency, and we're going to look mathematically that that's the case. If we are here, then what happens is, and this would be the limit, we get 2 samples per cycle. So you see the cycle starts here and ends here. So you get this sample and this sample for the first cycle. For the second cycle, you get this sample and this sample. And because we're exactly at the half of the sampling frequency, we get only exactly 2 samples per cycle, which means that if we connected the dots, now we get this triangle wave that is horrible looking if we compare it to the original wave, but still has the correct frequency and the correct information from it. The amplitude might not be right depending on where is the point that you connect, but it turns out that you can prove mathematically that it's still correct in amplitude still. Okay, cool. But what happens if the true frequency of the signal is above the frequency that we can sample? Because if you think about it, a signal can have any frequency, and pretty much any electronic signal would have frequencies that are up to the gigahertz range. I mean, this is not completely unfeasible. Even if you're sampling at a low frequency, let's say a few kilohertz, you still have gigahertz noise in the signal that is, due to electronic noise, due to picking up radiation from radio and whatever. So this content at very high frequency, it's still there in the signal unless you do something in the analog domain, which we'll discuss, which means that now everything else here that we can't resolve will, well, it has to appear in our spectrum because it still changes the location of the samples. So how does it appear? Well, this is why we're calling this the folding diagram, because what happens is the frequencies they fold, which means that now frequencies that are above the ceiling, they actually fold back into the resolvable frequencies of our spectrum, discretely sampled spectrum. Yeah, so this is the folding diagram. Okay, so if we look here, I could show a point over here, but it's kind of complicated to understand qualitatively. So I'm showing a point over here where basically we have the sine wave showing several cycles, and you see that we get a sample every cycle plus a little bit, which means that because we get this, this slippage of how many cycles we get just shy or just above a full cycle worth. It means that the phase of the samples is slowly shifting, and this gives us this effect that the frequency looks like it's signal but in slow motion. And so this is the phenomenon that we called aliasing before, and this is formally called aliasing for this reason. It looks like something that is very high in frequency. It looks like it's very slow, just because we happen to be sampling it in the wrong way, if you will. If we match exactly the sampling frequency, and this is the case where the droplets stand still, you can see that the sine wave, we take a sample every cycle, exactly one cycle, which means that we get a sample and then we miss everything inside the cycle, and then we get another sample exactly where the previous sample was, and then we get this effect where everything looks, every sample looks exactly in the same place, and it doesn't look like it's doing anything. So this is this example where the droplets look like they're standing still. And this folding diagram, it keeps on folding ad infinitum. I mean, as long as you have samples in your cycle, you get this. As long as you have these true frequencies in your signal that are above the sampling frequency over 2, then you get this effect of folding. So this is something that is very important to be careful about when you're performing sampling. And yeah, so this is kind of a qualitative explanation of what's called the Nyquist sampling limit. So I'm replacing here the half of the sampling rate by the Nyquist frequency, and this Nyquist frequency is defined as half of the sampling rate because it would be the limit of discretely sampling system. That would be the limit or the ceiling of the frequencies that it can resolve. Okay, so I would like to illustrate that this chart has upwards and downwards slopes, and this actually plays a very interesting role. So here I have this blue region where we got everything right. So we got both the frequency of the signal right, and we also got the direction of the signal, or the phase of the signal right. If we're in this red region, we get the frequency wrong, and we also get the signal, it appears to us to be going backwards. So we get the phase wrong, or if you will, we get a negative frequency. That would be another interpretation. And if you interpret it as a negative frequency, this line would actually start from over down. Actually, let me just do this. It would start from down here and then connect up here. So it would actually have a discontinuity here, and so this would be like this, whoops, and then like that. And I guess you got what I meant. So it would look like this kind of sawtooth wave instead. And if we are in this yellow region, then we still get the direction correct of the signal, but now we get the frequency wrong. So the frequency is actually between 2 and 3 of the Nyquist frequency, but we only can see between 0 and 1 Nyquist frequency. So we get the frequency wrong. So this would be the case of aliasing instead of folding, and that would be a this denomination is very loose. Some books use different things. Some professors differ in the denomination, but I think it's worthwhile mentioning that there is a difference between when you get the frequency and the phase wrong, which would be the case of the folding, and when we get only the frequency wrong but the phase correct, which would be the case of aliasing. Okay, so this ends the first section where we basically talk about the Nyquist sampling limit. And the only thing I think it's important to remember is that the Nyquist frequency is the sampling frequency over 2. And you see, this is important because when you're looking at an analog signal, let's go back here to this diagram. You want to make sure that your analog signal is free of all of this crap, because this is going to show in your spectrum, and it's going to affect your controller. Let's say you're controlling some physical system. This is going to affect your controller, but you kind of have to get rid of it. So in order to get rid of it, you have to filter it in the analog domain. This is important. You can't do any post-processing on it. You have to make something in your electronics, in your optics. Let's say you're sampling with an optical camera or something like that. You have to get rid of this in the analog domain. So in the case of electronics, you use a low-pass filter usually. In the case of an optical system, you would use like some sort of a filter that blurs the images. Like some piece of glass that is a little bit opaque. So that would be a way of getting rid of that. And of course, it might not look opaque to you, but it would be it would be applying this filter, low pass filter, in the camera, let's say. Okay, so this will end the first section, and now we're going to dive a little bit in the math. So we're going to talk about the discrete time version of the Laplace transform, and that would be the Z transform. That's called the Z transform in the literature. So the first thing we have to realize is that when we work, like in with the Laplace transform and we design our control systems in the S plane, that would be the analog plane, let's say, or the analog representation of our controller. And if we design the controller and we want to implement it in real hardware, like we want to use a microcontroller, we want to use an FPGA, or like if you're more of a hobbyist or a student, you might just want to use an Arduino, or if you're more on the industrial side, you want to use a PLC. What matters is you want to implement it in hardware, and nowadays hardware is going to be sampling the data and do some post-processing with the data in order to come up with a control input. And of course, this actually follows up on a previous lecture, but the S domain Laplace transform, it only applies to the analog domain. And the hardware that accomplishes stuff in the analog domain is just a bunch of op-amps. And so this would be like a prototype of how the set of op-amps, and I don't really know what this does, but it turns out that this is not very practical, and I think we evolved our solutions away from this, but now we have to deal with the problems that come from discrete sampling. So there's no problems with analog circuits. Actually, there's some implementations, very advanced ones, that do use analog circuits, but flexibility is very useful. So we can use an Arduino if you're doing it at the hobby level. If you're using an industrial controller, you might use a PLC or an FPGA if you're doing embedded, or a microcontroller if you're doing embedded. What matters is we want to make some representation of the filter function, the system that we're designing, which is our controller, in this case D of S. We want to represent it as something that works in continuous time but still samples the data. So what we want to do is fill up the box, basically. So let me just go back here. So this is just a closed loop control system, and you can see that we have the standard the nomenclature where we have a control input. We compare the control input with the measurement. We get an error. We apply a control out to this error, and then we get an output that goes to our plant, whichever plant it is. It could be a motor, it could be a tank, a heater, or whatever. And then the plant does whatever it does, and then it changes the control variable. The control variable goes back into the measurement device, The measurement device is also not perfect, so it also has its own transfer function, h of s. And then after the physical domain variable goes to the measurement procedure, it will become a measurement, which you can take the Laplace transform of the measurement. And then if you subtract the measurement from the desired value of the control variable, you get an error. So this is what we do. And this is very standard, but the thing is that we want to fill up the box such that we can do something in the analog domain. So let's open the box and try to do stuff in the analog domain. So I'm going to change the Laplace variables or the Laplace transformed variables for the time variables because I think it makes more sense when you're trying to learn this. And we basically want to fill up the controller scope. So we have the input, whatever the desired control we have, and also some measurement that we take, some sample in the measurement that we take, and we have an output. So we want to. The first thing we have to do is to convert this from the analog domain to the digital domain. And usually in electronic systems, we do that through a sampler. So a sampler is something that looks at the voltage of the analog domain, but it looks at it every once in a while. So this switch here represents this. I'm not going to look at R of t until I'm ready. And this until I'm ready, in this case, we're going to, because this is the simplest representation to go with mathematically, we're going to look at it every capital T interval. So the sampling period, capital T, would be constant in this case. And basically K would be an integer, and we get a signal R of capital K, K capital T. And similarly for the measurement. So we look at, whatever, let's say, for example, we have a potentiometer here, and we look at whatever the operator wants to do with this, and then we sample it, and here it would be the actual measurement. This here is less realistic, so we're going to get rid of it eventually. So after that, we take the signal through an analog to digital converter, an ADC, and that gives us a discretized version of R of kt. And I'm still going to call it R of kt because we're in this lecture we're not going to really discuss we're not going to really look into the effects of digitization in the controller. We're going to only focus on the effects of discretization, not digitization. So basically what I'm trying to say is that, let's say, for example, you have an ADC that is 8 bits, you can only have 256 values for R of kt. We're not going to look into that on this lecture. Okay, so let's move on. I'm going to remove that R signal because, let's be honest, in a digital controller, you don't really have an analog signal that you sample for the desired input. You actually usually have an operator typing on a computer or using a UI interface and clicking somewhere and saying, I want the temperature to be 20 degrees, or I wanted the system to go there, whatever the coordinate is. So it's more of a thing that happens in the memory of the controller. So I'm going to actually grab the R of kt from the memory. Okay, so then of course we have a program, and here I'm filling up the box. The program will blend the signals from R and M and do some calculations. So here we have R minus M, which is our error. And then this error is computed in some C program or something in the microcontroller, and then it will do some calculation, whatever it is. In this calculation, it might use the past errors or error measures. So you can actually have you can grab from memory some past measurements and compute some error, and then we do some calculation. And this calculation spits out, and I actually ran out of space, so let's increase the size a little bit. So this calculation spits out some number, some output that goes to our is intended to go to our actual system. Whatever it is, it could be a motor, it could be a heater. You get an output. So this output we're going to call U of kt. And after you do that, you actually have to go back to the analog domain. So in order to do that, the microcontroller or the FPGA or whatever it is, it will use a digital to analog converter, and it will also hold the signal. So if you update the signal, it's not going to update here and then immediately disappear. It's going to stay there. So this is what we call a hold. And usually we model this as a first order hold, which is basically hold it steady until you get the next sample. Okay, so I'm going to compress this a little bit. And these calculations, we're actually going to compress into the transfer function that we call d of z. Z is this discrete domain variable that we're going to discuss. And we're going to use this as a zero order hold. And here we're going to use the model this as a sampler. Okay, so let's plug this back into our analog system. And this is what we get, kind of in a summary. We get some computations. And the important thing to realize here is that we get some delay. So every time we make a measurement, we have to be done with our computations to actually pick it up. So we get a delay that takes as long as the computations take. Usually that would be at a fixed time interval, which means that we introduced a delay that actually plays a pretty big role in how the stability of the system works if you're too close to, let's say, the sampling frequency or the Nyquist frequency. Okay, so now we're going to actually dive in the math and talk about the discrete sampling and how we actually mathematically handle this. So the first thing we have to decide here is how we can mathematically describe some transformation that will help us work in this discrete domain. So we have here an analog function. This is some random function that, some random signal, f of t, and we want to take a sample. So how do we take a sample? So I think the reasonable thing that people use in mathematical descriptions that I think is very useful to accomplish this taking a sample procedure is to use a delta function. So if you multiply the function f of t by a delta function, it's like you're taking a sample. So for example, here I'm gonna play this little animation. When you multiply the two, you get just the delta function is 0 everywhere except at that point. So you get f of t times delta of t, which is just a dot. Okay, it's actually more formally defined as the summation, the integral of f of t delta t dt from negative infinity to infinity. But I think this suffices for this analysis here. Okay, but the thing is, this single sample is not really useful for us to define the signal. We actually need a constantly sampling system. So this system is usually called the Dirac comb, which is a set of Dirac delta functions that is evenly spaced by the sampling period, capital T. And this is how it mathematically is described. So delta of t minus capital Kt, where k is an integer from 0 to infinity, gives us this effect of discretely sampling. And, it's a Dirac comb because it kind of looks like a comb, if you will. And if we take the sample, one sample every t, we multiply the two together, and we get this, which would be the sampling effect on the function. And you see that we lost a lot of information, between as the function oscillated. And this is basically the stuff that we miss when we perform this sampling that gives rise to all of these problems that we're going to discuss. Okay, so now that we have this is basically the representation of our function in the discrete time domain. But it's represented in the physical time domain or in the analog time domain, which is great because now we can take the Laplace transform and it's valid. It's a valid operation. So if we take the Laplace transform of the sample function, so I'm going to use it as capital F of the fd, which would be the discrete function f. So we take the Laplace transform. This is just whatever it was before. Before we actually do the Laplace transform, there's a little trick we have to do here, because since f of t times delta of t, or delta of t minus kt, is defined as 0 everywhere except at the particular point of the sample, you can actually bring this f of t inside and do f of kt, and it's basically this would be a stair-stepped version of f, and you still get valid, or you still get this exactly the same mathematical representation. But this one is a little bit easier to handle, as we're going to see. So the Laplace transform definition is just the integral from 0 to infinity of e to the minus st dt. So this, or at least this is how I'm defining it. There's several definitions, but s is the Laplace variable, the complex Laplace variable that I'm defining here. And if we evaluate the Laplace transform, we can first realize that this part is not a function of t, so f of capital Kt is not a function of t, and this is why we did this trick. Whereas this part is a function of t, which means that now we can evaluate this integral. Basically, the Dirac delta function gives us the rise of this unit step, and it kind of makes sense, right? You have this Dirac delta, and you have e to the minus st. You just replace kt by t, and k capital T by t, and that's the only point where the function is defined. So when you do that, you get an extra ks t, k capital T times s into the exponent, and then you get the unit step because before the delta function you don't really have anything else. Okay, so we do have that, and then we have to realize that k is greater than 0, so we always have this unit step as 1, which means that we can get rid of it. And if we plug it back in, then the summation, we get this nice summation sign that is actually, we can handle this. So let's denote this f of capital K, k capital T as the nth sample. So this is f bracket n. So it's not f of n, it's f of bracket n, which is just the same notation for f kt. And if we make k the n sample, because this is just an integer, we can do this. And we're very close here because we know this is very close to the formal definition of the z transform. If we now introduce the dummy variable z, which is e to the st, then we get this, which is the z to the minus n goes here, and then f of n is just the nth sample, and we do the summation of all the samples that we have in the domain, and we get this f of fd of z, and this is literally the definition of the z transform. So if you don't remember anything else, you just remember that the z transform is defined as this, and it's useful. This definition is useful because it represents the process of sampling a function through a set of Dirac delta functions that is rather like what we do in practice, but it represents it mathematically, which means that we can actually understand what's going on. But at least when I was studying this, I didn't really get what this is doing, and especially what the z variable is doing to the complex plane. So I felt like we need to understand what the z transform is actually doing. So I made this little animation, kind of a la 3 blue 1 brown, and I just kind of a refresher. So this is the Laplace transform plane. In the Laplace transform plane, the real axis, which is the stick line, is it corresponds to exponential growth in the right hand side, and in the left hand side we get exponential decay because exponent is negative. If we go to the purely imaginary, which is called here the stability line, we get purely oscillatory signals. So if s is purely imaginary, the exponent is imaginary, which means that we get sine and cosine of some angle plus I sine of some angle, which is purely oscillatory. So the stability line is oscillatory, and anything that is a combination of the basically complex number will give us an oscillatory and exponentially growing or decaying. So if you're in the right hand side, you get exponential growth, oscillatory exponential growth. If you're in the left hand side, you get oscillatory exponential decay. And it's worthwhile highlighting here that in the case of the S-plane, where we're sampling, we actually have the Nyquist limit that is worthwhile highlighting. because this is the limit of our sample. We have stuff all the way up here and ad infinitum, but the only things that we should be able to see are to the Nyquist limit. And it's going to play a role when we perform the Z-transform. So the Nyquist limit in the S-plane is defined as I pi over t, which is just the oscillatory part of the sampling, plus some constant a, which is just some real number that lies in this line, in this yellow line. And of course, similarly for its complex conjugate. Okay, so I'm going to play the animation, and we are going to, let me see, yeah. And we are going to transition from the S-plane to the Z-plane. And this is a linear interpolation, but I think it gives us a very good sense of where stuff is going. So you see that the right-hand side is expanding, and the left-hand side is being compressed inside of the circle. Now now we're sitting in the Z-plane, and everything outside of this blue circle is unstable, whereas everything inside of the circle is stable. And you see that the Nyquist lines, they collapsed together into a single line at the left-hand side of the real axis. So this is a very interesting thing to note, because it basically means that we wrap the frequency domain of the S-plane into another plane that is also full, but now has it can actually have a multiplicity of frequencies. We're gonna discuss this later, but this actually spirals in, so you actually get several copies of the same frequency in the S-plane. So this mapping that we discussed in this animation is called a conformal mapping. And the conformal mapping, it maps the variable S, which is the complex Laplace variable, to the Z Laplace to the Z transform variable, and it basically deforms the complex plane. This is why it's called a conformal map. And there's a lot of interesting things to do. So let's examine every single one of them, because I think it's worthwhile to settle this. So at the stability line, we get S equals some imaginary number, omega, which is the frequency of this imaginary axis, plus 0. So there is no growth and no decay. If we apply z equals e to the st, we get z equals e to the I omega capital T. And e to the I omega capital T is literally a circle that of radius 1. So for any omega you get just a point in the circle. So this is at the unit circle. So if we now look at the positive real axis, where S is just some constant A plus 0 imaginary, and A is positive, then we do the mapping, and we get z equals e to the at. So e to the at is this section here, where it's always real and greater than 1. So it's outside of the unit circle, but still lies in the real axis. If we look at the negative real axis, we get the same expression, but now a is negative, which means that now when we apply the z-transform, we get z equals to the at, where a is a negative number. And since t is a positive number, we get this compression of a number between 0 and 1, because this exponential is always positive. So this means we get this little stub of line between 0 and 1. So it's always real, but less than 1. Okay, so now let's expand this to the entire left-hand plane. So if we have the left-hand plane, we have S equals A plus or minus omega I, where A is less than 0. So basically it's a complex number of arbitrary values, but now we're limiting our analysis to the negative A. So if we apply the Z transform, we get the Z equals e to the A capital T times e to the plus or minus I omega T. And if you think about it, e to the I omega T is just at the unit circle, as we discussed before. But e to the at, because A is negative, is always less than 1, between 0 and 1, actually. Which means that we're shrinking the circle to some other circle that is between 0 and 1. So this means we're always inside of the unit circle for the left-hand plane. So this is why the left-hand plane, the stable part, lies inside of the unit circle. At the right-hand plane, on the other hand, we get A greater than 0, which means that now we get the same mapping, but now A is greater than 0, which means that the exponential is always larger than 1 because a is greater than 0, and then you get you get e to the omega t, which is a circle that is now stretched to by some factor greater than 1, and this means that we get the any point or any circle outside of the unit circle. So the unstable region is always outside of the unit circle. Cool. And also, I think it's worthwhile discussing that, we also have the Nyquist limit, and the Nyquist limit has some interesting implications. So let's look at it a little bit closely. This would be this blue region. So the Nyquist frequency is 2 times pi times the Nyquist frequency. If we just divide 2 pi by the Nyquist frequency, which is the sampling frequency is 1 over t, 1 over capital T. The Nyquist frequency would be 1 over 2t. So when we divide 2 pi by 2t, we get pi over t. So that's actually why we get I pi over t in this expression that I discussed before. So this means that the s variable is any number, because we're not giving any limitation here of whether it's stable or unstable. The only thing we want to limit ourselves is to omega greater than the Nyquist frequency, or basically omega is greater than pi over t. So now if we look at the z transform, we get z equals e to the at, e to the plus or minus I omega t. But now omega is always greater than pi over t, which means that we can express omega as some number plus m pi over t, because pi over t is omega is always greater than pi over t, so you can always have it like as a remainder of the division of omega by pi over t, which is omega a, and then some integer times pi over t. And so this would be like, in a sense, doing a mod operator, if you will, where m is how many folds we get in the folding diagram, it turns out. So if we replace this back in z, we get this e to the plus or minus imt, which comes from here, and we get this e to the I omega at, which comes from this omega a. But this omega a is any number between 0 and the Nyquist limit. So this is what I would call the apparent radiant frequency, whereas this number here is either 1 or minus 1. So because this is either 1 or minus 1, we get this expression where we get the minus 1 to the m, and then this is basically what it was before. So this number here gives us whether it's a fold or an aliasing. If m equals 1, we get one fold, which means that minus 1, we get a negative sign from here. So this negative sign means that we get the phase wrong. If m equals 2, then we get minus 1 squared, which means that we get 2 folds. And as we saw in the folding diagram, 2 folds means we get aliasing, where we get the phase correct. And this is consistent here because we get minus 1 squared, which is plus 1. So we get exactly the same as the apparent frequency. It's just that the apparent frequency is wrong. Okay, and this is basically a discussion that I gave here. So if we compare this with the case inside of the Nyquist limit, where we get the same exponents, then we see that the frequencies above the Nyquist limit, they just wrap around. So let's look at this in the animation again. So here I'm removing all the labels and I'm just showing the raw animation. And you see here that there's actually stuff above the Nyquist limit now. So we actually have one extra fold in the folding diagram. So I'm going to play the animation. And as you can see here, the fold actually, it's a little bit overwhelming, but you can see that it actually wraps around and it eventually is going to collapse into the same exact frequencies. So you see, it looks exactly the same, but now we have one fold up and one fold down. So this is rather interesting and rather, for me at least, it explains why the Z-transform is so useful in defining the behavior of a system for a control system that discretely samples the system. Okay, so we'll look through all of this math. So this is this is the end of this section, and I think by now you're probably overwhelmed. And you probably, if you're more on the engineering side, you're gonna say, "I just wanted to program my Arduino or whatever device it is," right? And I agree. I think it this all of this math is beautiful, but it's not useful if you can't apply it. So here I'm going to do a little section on how to actually make this Z transform work. So let's say you wanted to program a PI controller on your Arduino. So if we go back to the Laplace transform definition of the PI controller, we get D of S is some constant of proportionality plus some constant, the integral constant divided by S, because well, 1 over S is the integrator. And we can represent it as this fraction if you want. It doesn't really quite matter. But what we can realize is that the controller is doing a filter, is implementing a filtering function. And this filtering function, it grabs the error, which is this E of S, and it applies this filter, and then it gives us some U of S. So it's in this case it's smoothing E of S. And this is rather important to see. So the control input is just a smoothed version of the error signal. So, and of course, each controller will do something else. So if we will, another way of interpreting this is that this function is a differential equation that describes how the control input changes as a function of the error. So this is how I would express this as a differential equation. So if you see here, I moved the E of S to here, and then I move the S to here, and we get S E of S equals KPS times E of S, and then KI times E of S, and then this division by KP cancels out, so you get only KIES. And if we go back to the time domain, well, how do we do that, right? So you know that the multiplying the Laplace transform of a variable by S gives us its derivative, so this is U dot. And we get here S E of S, so we get E dot. And here we don't get any dots because we don't have any S's. So this is what we call the velocity form of the PI controller, where we're basically equating the velocity of the output variable U as a function of the velocity of the input variable and its current value. And this is somewhat useful, but it's a little bit difficult sometimes to implement. So I think the position form is a little bit easier to understand. So we integrate the equation. So we integrate this from 0 to t, and we get U of t. We integrate this, and we get E of t. And we integrate this, and we get the integral from 0 to t of E of tau d tau, and this is just a dummy variable for the integration sake. And this is what we would call as the position form of the PI controller. But one thing that we have to realize is that we can't really compute this integral because it's a continuous integral, right? This integral here happens in the analog domain. And the only thing we have is samples. So the only thing we can do is approximate the integral by using our samples. And we can do that in a lot of ways. So let's look at this a little bit further. So let's say we're sitting here at 11t, and we want to approximate this integral. So there's three methods that we can use, or at least that are easier to look at in the literature. One is called the forward Euler difference scheme, which is also called the forward rectangular, backward Euler, and Tusting's rule or trapezoidal integration. And basically, the difference between them is what do you do to the samples. So in the forward Euler scheme, and let me actually grab my pen here. So in the forward Euler, you're integrating forwards, which means that for this point, I actually make a little rectangle, and I compute this area, which is just whatever the value times capital T. And I do that for every single one of them, right? So this one would be this little rectangle here. This one is this rectangle. And I keep on doing that. But one thing that is worthwhile mentioning is that I have 11 samples. Sorry, I have 11 timestamps, but I actually have 12 samples. The first sample is 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 samples. That's what I meant. Whereas we only have 11 intervals. So if you look at the intervals here, this is 1t, 2t, 3t, 4t, all the way to 11t. So we have more samples than time intervals, which means that if you compute the summation of the whatever e of t, or in this case e of kt, and then we multiply this by capital T, right, which is the number of the time delay between the samples, from k equals 0 to, in this case, if you went all the way to 11, you would get 12 samples, but you have to divide by 11 timestamps, which means that we actually have to stop at 10. So in the forward rectangular rule, you drop this point. And this is a rather important remark to make. So this would correspond to the forward rectangular rule. If you look at the backward rectangular, it's exactly the same procedure, but you don't drop this point. Let me erase it to kind of represent that. You actually drop this guy here. Let me grab the pen. You drop the 0th point. So in that case, you get 1 over 11t, but the summation, and I apologize for this, I'm using my mouse, is from 1 to 11 of e of kt capital T. And capital T is like our dt in the integral. So this would be backwards. We can also use the Tusting's rule or the trapezoidal integration. And the trapezoidal integration is rather interesting. So let's look at it. So let me erase all of this. So you probably heard about trapezoidal integration before. And the trapezoidal integration, it uses the two samples, connect them together with a line. This is supposed to look like a line. And then it computes the area of this little trapezoid. And it does that for this one. And it does that for every single one of them. So you get an integral that is a little bit more accurate, if you will. So in the case of the trapezoidal rule, you actually do get to use all of the 12 points. So let's write out the equation for it. So it's 1 over 11 capital T of the summation of k equals, and here you can do whatever you want. You can do 1 to 11 or 0 to 10. The only thing you have to be keen of is that you actually sum e of kt. So in this case, you're summing e of kt minus t, which is the former sample, with e of kt. You divide that by 2. So this would be the average between the two samples, which is how you compute the trapezoidal integral. And then you multiply that by t. And in this case, I'm using 11 because I think it's a useful number, to kind of make it concrete. So this would be Tusting's rule. We're going to discuss a little bit about this and some of the implications. But in this particular discussion, we're going to be looking at the backwards Euler integral because first, it's a little simpler. And second, it actually has embedded on it some causality, which the other two, they don't really have causality embedded on them, which means that you have to shift back one sample. And this is something that is a little bit annoying in the math. So the backward Euler, I think, is the good introduction for this. So let's approximate a derivative with the backwards Euler integral. So the derivative is just this. In the case of the backwards Euler, you get the current sample and the backward sample, and you just compute the derivative. In this case, the derivative is the difference between the samples divided by the distance between them, which is capital T. So this would be e dot of 11t is e of 11t minus e of 10t. And if we generalize this expression for any capital K, any k, you get e dot of kt equals e dot of kt, which is the current sample, minus e dot of kt minus t, which is the former sample, and you divide 2 by t. And this is a comment that I was trying to say before, is that the real controller, the controllers that we implement in physical reality, they are causal, which basically means that the controller can't really predict the future. Or if you go back, actually, let me go back to this. We can't really use the future sample because we don't really have access to it, right? So the future sample is not available to us. That's why I think backwards Euler is the more reasonable way of performing this integration. And of course, this is in contrast with some offline filters. In the case where you're implementing an offline filter, you can actually have the future data because all of the data has been captured. So the transfer functions of forwards Euler, for example, are actually reasonable in that case. Okay, so let's go back to our PI controller. Apologize for that. And let's look at our differential equation. U dot of t equals kp e dot of t plus ki e of t. And I'm going to use the velocity form because it doesn't really quite matter. The two actually arrive at the same equation. And I think that the velocity form is a little bit easier to understand. And I personally, when I'm designing controllers, I use the velocity form for the design. So let's go through this. So if we use u dot of t, we perform the finite difference on the backwards Euler scheme, and we get u of kt minus u of kt minus t. We do the same here. And for ki, we don't do anything, so we just use the current sample, which is e of kt. So we're going to replace these kts by n. And this is just because we want to relate to the z transform. Remember the z transform. So this is the nth sample of u and the n minus 1th sample of u, and similar here and here. So let's crunch a little bit of the numbers. So I'm basically trying to isolate u of n, which is the next input. And if you look, if you just move around capital T to here, you get this expression. And you can convince yourself this is the case. But there is an interesting point about this expression. Since we isolated the value of the current output as a function of the current measurements, past measurements, current measurement, and past outputs. This means that we now can compute the next output of the controller with data that we can store in memory. So we can actually implement that expression, let's say, in our Arduino. So how would this work in practice? So let's say, for example, we have here our memory, and in the memory, in this case, we would have to store the values of the current error, which would be based on the current measurement, and the error of the last sample, and we also have to store the measurement of the last cycle, if you will. So this is easy. These are variables that you can have in your memory, and the program literally just has to compute this expression. And since all of these values are in memory, it's simple, right? It's just a math operation, actually a very simple math operation. After you do this, you come up with a new control input, u of n, and now this would basically be the end of the for loop. You just give this to your output stage in your Arduino, update the outputs. And then after you update the outputs, you update the memory. And then you close the for loop, and in the next round of the Arduino for loop, you would be looking at the memory again, but now with the updated values and the updated measurements. And you just keep on doing that over and over again, and that would be the implementation, the physical implementation of the controller. So this is a very simple C implementation that you can do in literally 5 minutes. So, okay, but the cool part about the Z-transform representation that we have for U of n is that now we can actually understand what this control law is doing. So let's take the Z-transform of all of this. So the Z-transform works pretty much like the Laplace transform. So if we use the z transform of u of n, which is the time domain u. If you transform it, you just get u of z. Similarly for e of n, but there's here a little trick, and this is a trick that you can look online. But when you're taking the z transform of the last sample, you get an extra 1 over z, or z minus 1, z to the minus 1. And this is the side note that kind of proves how this is the case, assuming you have 0 initial conditions. You just kind of prove that if you take the z transform of the u minus 1, you have this expression, and you go through this math, and you get, you get a time shift of one sample, and you get z to the minus 1. And this actually helps, this actually works for any shift. So if you want to shift by, let's say, k samples, you just have z to the minus k. Okay? And if you want to shift forwards, you get z to the plus k, but that would not be causal, as we discussed. Okay, so now we're going to shuffle around a little bit in the math, and we're going to kind of isolate the expressions here. So I'm bringing this to the left-hand side. I get this 1 minus z to the minus 1. I am isolating or putting in e of z in evidence, and then I get kp minus kpz minus 1, and then kit, which goes here. And I'm going to multiply everything by z. So I get z minus 1 instead of u1 minus z minus 1. And I do the same here and here, and we get this expression. And the last thing we need to do is to compute the transfer function, which is u of z divided by e of z. And this transfer function looks like this. And because the z transform has this nice transfer function, we can actually determine whether this is stable or not. So let's say, for example, here, if we go back to the definition of our controller in the S domain, we have this, which means this controller here has a pole at 0, which is this pole here, and it has a 0 at minus ki over kp, which is this guy here. And so this means that we have a controller that has a 0 in the stable region and a pole at 0. So this controller is very unlikely to destabilize a system. I mean, if the system is already stable, it will not destabilize the system. It's kind of hard to prove here, but it's kind of guaranteed that this will never destabilize the system. But if we look now at the controller in the Z domain, this controller has, again, a pole at z equals 1, which is this pole here. And this would be exactly the same understanding. So if the pole at 0 here actually goes to z equals 1 here, but it also has the 0 that is at a slightly different location in the z-plane. And this actually does play a role. So let's actually go, and this is kind of a simulation that I did in MATLAB just to kind of show what actually happens to the poles. So for example here, as this is the root locus diagram on the continuous system, which is in the left side. So these are the parameters if you want to reproduce this yourself. So this is the plant poles are stable, as you can see here, and these are the poles added from the pole and the 0 added from the PI controller. And if you close the loop and you increase the gain, this would be the root locus. As you increase the gain, you go along this line, and as you increase the gain, you go along this line. You see that the pole becomes more and more, let's say, towards the unstable part of the diagram, but never crosses the line. And this is what's important about this. It basically asymptotes, so it becomes less and less damped, but it never actually becomes unstable. But if we look at the same system, now sampled at a sampling period of 0.1 seconds, then that system, and this is something that I forgot, you also get zeros at Nyquist. So in the case of a second order system, you get 2 zeros at Nyquist, which means that now the plant poles, they actually go around this big circle that is larger than the unit circle, and one goes here and the other goes there. So this effect of going around basically means that if you increase the gain too much, you're outside here, which means that your system becomes unstable. And that's, of course, just because the sampling period is is too slow for the reaction of the plan. Because if you look back in the continuous domain, you can see that as you increase the gain, your system responds with a higher and higher frequency, which means that now your controller has to have more bandwidth to actually control it, keep on controlling it. That's kind of a more loose interpretation of how this works. And if your controller doesn't have that bandwidth because it's sampling the samples discretely, then your system becomes unstable. That would be, I think, my take on it. Okay, so I think this is enough. This is long enough, definitely. And I'm just going to finish this by kind of summarizing what we looked at. So we went through the Nyquist limit, the folding and aliasing effect, and we looked at the folding diagram. I think this is a rather important diagram to have in your mind when you're designing control systems, and especially when you're filtering your signal to make sure you get rid of all of this crap, because this hurts your controller's performance. If you think about it, if you're trying to make a controller and your frequency is here and it appears here for your controller, it's trying to control something that is not really controllable for the controller, which means that, well, it's going to fail and maybe even make the system unstable. Then we looked at the Z-transform, and I think that the Z-transform definition is rather important and something to remember when you're doing these calculations. We looked at the Z-plane and how this mapping occurs, the folding of the complex S-plane into the Z-plane, which is a polar mapping, and how it folds back and forth in a kind of a spiraling way. So this actually goes on and on in both directions, which causes the aliasing phenomenon to begin with. And then we did a discrete integration to kind of practically exemplify how we actually go about implementing these kinds of controllers. So with this, I would like to end this, and I appreciate if you stick around. And if you want to look more into how to build the piddler device, you can check out the website in the link. So thank you so much for watching, and I'll see you next time.